Hello friends, I am Professor D.G. Trivedi going to take your lecture number 7 in using the method of separation of variable. We are going to study another problem in a Cartesian coordinate system. We have studied one problem in a Cartesian coordinate system, that is solving the Laplace equation in 2 dimensions. This is also almost similar problems in 2 dimension only with the azimuthal symmetry. So the problem is like this. Two infinitely long grounded metal plates, again at y is equal to 0 and y is equal to a, are connected at x is equal to plus minus b by the metal strip maintained at a constant potential V0 as shown in the figure 3.20. A thin layer of insulation at each corner prevents them from shorting out. Find the potential inside the resulting rectangular pipe. You can understand this saying from the figure. This is your figure. This is XYZ Cartesian coordinate system is going to be there. This is x-axis, y-axis and z-axis. So there are two infinite conducting plates. One at y is equal to 0, another at y is equal to a. They are grounded. That means their potential on a conducting plates are going to be 0 everywhere at y is equal to a and y is equal to 0. There are two another conducting plates. One from here, if you can see that at x is equal to plus b and x is equal to minus b, there are another two conducting strips are there, but they are not potential 0, but they are maintained some constant potential V0 here also, V0 here also. And at the corners, all corners, they are insulated with the top plates as well as from the bottom plates. So they won't be shorting out with top plates or bottom plate because they are maintained at another potential grounded or 0. So it should be insulated. So this is the things. In our previous problems, this side x tends to infinity, that was the fourth boundary. Here the third and fourth boundary are finite. That means x is equal to either plus b or x is equal to minus b. And you can see that you have to find out the potential, the function of the potential in this region of the space, that is the function of xy, and hence again this is a 2 dimension problem. So the configuration is independent of z, so this is really a 2 dimension problem. And mathematical terms, we must solve the Laplace equation del square v upon del x square plus del square v upon del y square. This is equal to 0, subject to the boundary conditions. V is equal to 0 at y is equal to 0. V is equal to 0 at y is equal to a. V is equal to V0 at x is equal to plus b and b is equal to V0 when x is equal to minus v. You can see that this is maintained. X is equal to plus v and x is equal to minus v. The potential is V0 and x is equal to y is equal to 0 and y is equal to a. The potential is 0. So all the boundary which is surrounding this region of the interest, the potential is specified, and hence we can solve the Laplace equation in 2 dimensions. Now this is almost similar to the previous problem until the general solutions. Until we apply the boundary conditions, the problems are going to be the similar. You have to move in a similar fashion, because once you are solving the Laplace equation del square v is equal to 0 in 2 dimensions, the general solutions is going to be obtained similar way using the method of separation of variables. So I'm just revising this thing little bit so you will understand it's better way. The things which we have done in a previous problem, the same thing we are going to do it here also. You can see that since the potential is specified on all the boundary, answer is uniquely determined. The first step is to look for the solutions in the form of products. That means in a region of interest, in this slot, rectangular slot, the potential V is a function of xy can be thought as it is a product of the two functions which each function depends upon one variable only. Capital X is a function of small x, capital Y is a function of small y, where each function depends on one variable only. Just like previously, we are moving in the same way. So I'm just telling you so you understand that what is the method of separation of variables. Anyway, putting equation 3.22 into this, we obtain capital B is equal to xy, that we are substituting here. And because when you are differentiating xy with respect to small x, then y is going to be constant, it is taken out. So y into d square x upon dx square plus, similarly here, the xy, when you are differentiating with respect to y, then x is going to be constant. So it is taken out, and that means the equation is going to be reduced into this form: capital Y into d square capital X upon dx square plus capital X into d square capital Y upon dy square. This is equal to 0. Now, we are going to separate the variables. That means this both the terms we are going to divide by v is equal to xy. So the first term, when it is dividing by xy, y will be cancelled out. Here it remains 1 upon capital X. Again here, x upon xy. X is going to be cancelled out, 1 upon y remains. So you can say that equation reduced to like this one: 1 upon capital X, d square capital X upon dx square plus 1 upon y, capital Y, d square capital Y upon dy square. This is equal to 0. Here, the first term depends only on x and the second term depends only on y. In other words, we have an equation of the forms: first term entirely depends upon one coordinate, small x only. Second term entirely depends upon the second coordinate, y only. That means we have separated two terms which are depending upon single variable only. This can be written in this form. That means the first term is nothing but f is a function of x only, and the second term, which is another function, g is a function of y only. So fx plus gx, that is equal to 0. We are getting in this form. This is only true because both are functions, both are depending upon independent variables x and y. So in only one case it is going to be true if f and g both must be constant. Now there is only one way this could possibly be true: f and g both must be constant. It follows from the equation 3.23 then that 1 upon capital X d square capital X upon dx square is equal to c1, and 1 upon capital Y d square capital Y upon dy square is equal to c2. Substituting this, we'll get that c1 plus c2 is equal to 0. Here one of the constant is going to be positive, another one is going to be negative. One of this constant is positive, the other is going to be negative, or perhaps both can be 0. So we can consider that, let us say C1 is going to be positive and that is equal to k square, and C2 is going to be negative, that is equal to minus k square. Substituting this, we'll get d square capital X upon dx square, that is equal to k square capital X, and d square capital Y upon dy square, that is equal to minus k square y. A partial differential equation has been converted into two ordinary differential equations, and solutions of these two ordinary differential equations are easier. We can integrate 2 times and you will get the solutions of capital X as a function of small x. Here also similar way, you integrate 2 times and you will get capital Y is a function of small y. Here the constant is going to be positive, the solutions of this is going to be exponential solutions, and here the constant is going to be negative, the solutions is going to be sinusoidal solutions. The advantage of this is obvious. Ordinary differential equations are a lot easier to solve, and hence we get a general solutions of this second order ordinary differential equation, that is exponential solutions is going to be there. So capital X is a function of small x, that is equal to capital A e raised to kx plus capital B e raised to minus kx. This is a exponential solution, general solutions. A and B is the constant of integration. Similarly, y is a function of y, that is equal to c sin ky plus d cos ky. So our general solutions is this: capital V, that is a potential inside our slot, is a function of x and y that is equal to product of these two functions. Hence, a e raised to kx plus b e raised to minus kx into c sine ky plus d cos ky. So until to this, everything is going to be common for the problem number, the previous problem or this problem for the two-dimensional Laplace equation. This is the appropriate separable solutions to the Laplace equation in two dimensions. Now it remains to impose the boundary conditions and see what they tells us about the constant. So now, after getting these general solutions, what we have to do? We have to obtain the specific solutions to our problem. And for that, now whatever the boundary condition is given, that means the potential is specified on all boundary of the region of the interest, that one by one we have to substitute and we have to understand the constant of integration a, b, c, d, etc. This time, however, we cannot set a is equal to 0. The region in question does not extend x is equal to infinity like previous problem. Our fourth boundary, that means x tends to infinity, potential tends to 0 was there. And then we could set that a is equal to 0. But now the x is not going to be infinite. X is going to be finite. X is equal to plus b or x is equal to minus b. And hence we cannot say that x a is equal to 0. So we have to find out here what will happen. So in that equation, if we substitute here, in this equation, if x is equal to, if we are substituting in first boundary conditions, that means x is equal to b, then v by is equal to a e raised to. For wherever x is going to be there, we'll substitute b here. So a e raised to kb plus b e raised to minus kb into this thing as it is. And this is equal to the potential v0 is there. Similarly, if we substitute x is equal to minus b, then v minus vy, that is equal to again a e raised to k minus b plus b e raised to minus k minus b, that is going to be plus b. So both the equations are almost going to be same, and this indicates that a is equal to b. It remains to impose the boundary conditions and see what they tells us about the constant. On the other hand, the situation is symmetrical with respect to x. It means x is equal to plus b or x is equal to minus b. The potential was v0, and that tells that v minus xy, that is equal to v plus xy, and it follows that a is equal to b. So now if we substitute a is equal to b in these equations, that means a and b can be taken out, and that is going to be capital A. And inside the bracket e raised to kx plus e raised to minus kx will be there. And if we divide by 2, then 2 is going to be multiplied with the a. So 2a into e raised to kx plus e raised to minus kx upon 2. And that term inside this bracket is equal to hyperbolic function, and that is equal to cos h kx will be there. So this we can substitute here, and absorbing 2a, which is a constant, into the c and d, we get vxy is equal to cos h kx. That is for this thing. And c sine, because 2a is going to be multiplied with the c and d, so c sine ky plus d cos ky. Now imposing the boundary condition 1 and 2. What was the boundary condition 1? Just like previously, potential was 0 if y is equal to 0. So in this equation, if we substitute y is equal to 0, sine 0, that is going to be 0 anyway. So even if c is going to be 0 or not 0, that this term is going to be 0, but this term will not be 0, because cos 0 is not going to be 0 unless d is going to be 0. So the first condition tells that d has to be 0 to make the potential is going to be 0 when y is equal to 0. And the second conditions require that y is equal to a, then this term is going to be 0 when this ka, that is equal to n pi. where n should be some integer. It indicates that the value of k should be n pi upon a, where n should be some positive integers 1, 2, 3, etc. Then this term is going to be 0. So this conditions, the boundary condition 1 and 2 requires as before that d is equal to 0 and k is equal to n pi upon a. So substituting this value of k into these equations, and Vxy is equal to Cn cos h n pi x upon a sin n pi y upon a. Here we have substituted the value of k n pi upon a in place of k here as well as here, and that is the equation 3.41. But because Vxy is even in x, it will automatically meet the boundary condition 4 if it fits the boundary condition 3. Because boundary condition 3 and equation boundary condition 4 are symmetrical about the x is equal to plus b and x is equal to minus b, the potential is same. So if it can fit the boundary condition 3, it can fit for the boundary condition 4 also. Therefore, it remains to constitute a general linear equations, because we are from these conditions that k is equal to n pi upon a, where n is the positive integers 1, 2, 3. So we are not getting a one solutions, we are getting a set of the solutions. We are getting a family of the solutions, and none of them by itself fit the last boundary conditions, but we'll get the most general solutions because the Laplace equation is having a property of completeness. So using the property of the completeness, if the v1, v2, v3, etc., is the solutions of this equation, then the linear combination of them, that is alpha 1 v del square v1 plus alpha 2 del square v2 plus etc., that is also the solution. So we can say take the summation that Vxy is equal to summation of n is equal to 1 to infinity Cn cos h n pi x upon a sin n pi y upon a is supposed to be the solution. Now, this is not directly actually satisfying our third and fourth conditions, but in this one there is a one coefficient Cn which is already buried in this one, and that value of the coefficient we have to find out so it can satisfy the last two boundary conditions. And to pick up that last coefficient which is buried in this sine series, we have to utilize the Fourier trick. So we can substitute x is equal to b. So by is equal to sigma n is equal to 1 to infinity Cn cos h n pi. In place of x we have substituted b upon a sin n pi y upon a. This is equal to 0, and this is nothing but this is all constant. So this is going to be the sine series or Fourier sine series will be there, and this is going to be equal to the constant potential V0 is there. So this is the same problem in Fourier analysis that we have faced before. So using the Fourier trick, we can solve this thing and we'll find out the value of the coefficient Cn which is buried in the Fourier sine series, so that when we substitute it in this one, they will satisfy our condition 3 and 4. So we'll get the specific solutions to our problem. So using the Fourier trick, we can multiply this equation, both the side, left hand side as well as on the right hand side, by sin n dash pi y upon a, and integrate in the limit from 0 to a. Now, when we do these things, what will happen? If we integrate this side as well as if we integrate on this side from integration from 0 to a sin n dash pi y upon a, then what we are getting? We are getting that there is only one term for this integration on the left hand side, integration from 0 to a sin n dash pi y upon a sin n pi y upon a. Here this is using the function of orthogonality. We can say that this integral is going to be 0 if n is equal to n dash, and this integral is going to be a by 2 if n is equal to n days. So there is only one term in this summation is going to be survived where n is equal to n days, and all other coefficients are going to be drop out, and only one coefficient which is going to be there with that integration, that is going to be n is equal to n days. So this side, on the left hand side, we can say that Cn cos h n pi b upon a into a by 2 will remain. So left hand side reduced to a by 2 Cn cos h n pi b upon a remains. It means that our coefficient Cn is equal to 2 upon a cos h n pi b upon a integration from 0 to a v0 sine n pi y upon a dy is going to be there. And this integration is going to be a 2 by n if n is odd, and this integration is going to be 0 if n is going to be even. I got the result from the equation 3.35, that this means Cn cos h n pi b upon a is equal to 0 if n is even, and this is equal to 4v0 n pi if n is going to be odd. And hence the value of Cn is equal to 2 upon pi cos h n pi b upon a, the integration from 0 to a v0 sine n pi y upon a dy. This is equal to 0 if n is equal to 0, and this value is equal to, here this constant is going to be multiplied by 2 upon n. So 2 into 2, that is going to be 4, and this is going to be v0 upon n, and this is going to be integration. It comes out to be pi n cos h n pi b upon a, where n is going to be odd. Substituting this, we'll get a general solutions. That means our solutions, whatever you have seen here, this is your general solutions. Vxy is equal to sigma n is equal to 1 to infinity Cn cos h n pi x upon a sin n pi y upon a with the coefficient given in the last equation which we have obtained. We can substitute that one. This is the value of coefficient Cn. If we substitute in this one, we'll get the final solutions, and that final solutions is going to be this. That means v is a function of xy is equal to 4v0 upon pi. Now for the n is equal to odd only, this integration was survived, and that's why here you can see that limit for n is equal to changing 1, 3, 5, 7, etc. That means n should be odd only. N is even, then this is going to be 0. 1 upon n, this is the value of coefficient, that is cos h n pi x upon a sin n pi y upon a, and this is the value of Cn we have substituted here. So cos h n pi b upon a. So this way we can obtain a specific solutions to our problem, and this is the graphical representation of the equation which we have obtained. Thank you very much, friends.